So when there are covalent molecules, covalent compounds, we have to figure out how they're going to be named. It's not going to be the same rules, different rules than we use for naming ionic compounds. What we're going to be able to do is make some generalizations according to what components there are. When we say binary, that means just two elements combining in the compound. And so we'll have to decide which one is more cation-like or more anion-like. In other words, the one that's electron poor is described as more cation-like, and the one that's more electron rich, has more electrons around it in a general sense, is going to be the one that's listed in a different way. So the cation-like element first is going to be the first part of the name. It's also going to be the one that's more left on the periodic table. And the other element is going to be second, changing its ending to an IDE, and it's going to be the one from the right side of the periodic table, given your choice. So thankfully, you kind of read from left to right, and the names are going to be just two words put together. Thankfully, these aren't really too hard, but you just got to pay attention to when they're covalent, that they're using this set of rules. Typically, covalent and molecular compounds, same thing, are going to be nonmetals, combination of nonmetals. So primarily a lot of things on the right side of the periodic table. And so there are only so many elements that are typically involved in these molecular compounds. The nonmetals also include hydrogen, of course. Don't overlook hydrogen. We sometimes forget where it belongs. So when these things are combining, they're just nonmetals, and there's all kinds of different proportions that they come together in creating compounds. And so you cannot predict what the proportions are going to be by looking at their position on the periodic table. There's lots of different ways they combine. So you have to include details. Numerical prefixes are going to be needed in a name to tell us how many things are part of how many atoms there are in a particular compound. So the prefixes that are used are not too tricky. You won't run into all of these all the time, but some of these will come up now and then. So mono, di, tri, tetra, penta, those things all kind of make sense. They feel like prefixes that might relate to other things you've heard of, like pentagons and hexagons. Heptagons don't come up. Octet, octa, whatever is the shape of an octagon, like a stop sign. Deca means 10. So those prefixes have some familiarity in other contexts, thankfully for us, in our common usages. So in a general sense, you have to add a prefix to the front of each element name to tell the number of each atom. So in the case of N2F4, you're going to have a prefix that tells us there's 2 nitrogens in the compound, and 4 is tetra, 4 fluorine in the compound. 2 words. The second one ends in IDE because it's the more negative, more anion-like, and just like we did with ionic compounds, anions were going to be simple ones, were named with IDE endings. Very related, but in this case, we know it's covalent because these are 2 nonmetals. Nonmetals are going to make covalent compounds. Another example is N2O4. So the first element is listed as more cation-like. It's also on the left of the other one. And so the left one is the one that's getting listed first. It's going to take the name of the element unchanged, but in this case, we add a prefix to tell us how many of them are present in the compound, so it's dinitrogen. The second element in the compound is the more anion-like of the 2. It's more on the right of the other in the periodic table. That works. And it takes on an IDE ending to tell us that this is the second element in the compound. And the prefix that tells us how many there are will be tetra. So dinitrogen tetroxide. Whenever the prefix ends in a vowel, A or O, like tetra or something like that, and the element name begins with a vowel, we will drop out extra vowels, A's and O's, in the prefixes so they don't get clumsy to say. So tetra ends in A, but we'll drop the A and call it tetroxide. And another case is if we have a prefix for the first element is mono, we will typically drop it. So you've heard of carbon dioxide, but we don't say monocarbon dioxide. We just say carbon dioxide, or carbon monoxide is its analog with just 1. So don't look for too many vowels piled up in these names. They won't need them. All right, so let's name a couple examples. So we have two things with cute little pictures, and we'll talk about their shapes later, but for the time being, you can tell that there is a phosphorus, if that looks purple to you, it's kind of funny color distortion, and it's surrounded by 1, 2, 3, 4, 5 chlorine atoms. And so which one is going to get listed first in the name is the one that's closer leftmost in the periodic table. It's PCl5. And so the name that goes first, the element that goes first is the leftmost one, which is the same as the way it is in the formula. So that's phosphorus, no prefix needed because there's just one. And if there's 5 chlorine atoms in that compound in the molecule, then we're going to say penta, and then chloride is the ending for that chlorine in that molecular compound. Same as it would be in an ionic compound, but we can tell it's a covalent compound because it's got prefixes. So prefixes only for covalent compounds, never in the other one. Covalent compounds only. You never need them for ionic. The second compound on the right has 2 nitrogens that are shown in blue, and red is shown for oxygen. And of the 2 elements, nitrogen is left, so we'll list it first in the formula, N2O. And N2O, well, what would you call that? We have to be descriptive. So the first one has to be described as dinitrogen, and its friend is just oxide. There is not more than one, and you don't have to say monoxide. It's dinitrogen oxide, or you could say monoxide. Both are possibly going to be used. So dinitrogen and monoxide will be completely clear. But then we don't put in 2 O's, it's just be monoxide without putting 2 in the middle. This is probably preferred. Sometimes you'll see both. All right, now the other ones that we need to name in this section and is in our learning objectives for this chapter is other binary compounds, in other words, just 2 elements, but these are described as hydrocarbons. Hydrocarbons are simply combinations of carbon and hydrogen. And some of these are things you may have known from common occurrences. You may have heard of methane, which is like what's in natural gas. And you might have heard about propane in your gas grill. And you might have heard about butane in pocket lighters or whatever it is your gas grill needs when your automatic starter doesn't work. So these are names that may have come along. They're called alkanes. Means that they all have only single bonds between the carbons and the hydrogens and the carbons too. So that's what this type of category of compounds is known as, is alkanes. The thing is, to make sure we understand the names, it's again going to look like root words that we used in prefixes a minute ago, but not quite the same roots, that are going to be descriptive to tell us how many carbons are present. So when you have 1 carbon, the prefix is going to be meth for methane. When there's 2 carbons, it's going to be ETH, and they all end the same ANE ending. 3 carbons is propane, and 4 carbons is butane. Some of my students have loved to remember this by thinking in terms of the first letters, and a mnemonic device, me, eat, peanut, butter, puts them in the right order. They all have single bonds, and the carbons are connected together. We can draw these in more than one way, and some of these are just molecular models. The formulas are over on the left, but if we draw them out completely, and we'll do more of this as the chapter goes on, the carbons have to be connected to each other, and then the rest of the hydrogens fit around each of the carbons. So methane, ethane, propane, butane, the rest of them have names that feel more like a root word that makes some kind of sense to you. Pentane, in fact, has 5 carbons, and so if you drew it out, you have the carbons all have to be attached to one another, and the remaining atoms are the hydrogens, in this case 12, and if you put them all around the carbons in a fashion that every carbon gets 4 bonds, which will become more obvious later, you get the correct structural formula for these compounds. So the structural formula will be something we do in the next section of the chapter. So the pentane is for 5 carbons, but we need to know the rest of them. We need to know the first 10, and these are topics out of chapter 23. So if you've got the e-text, you can pull it up there. This is a different chart than that one because it fits on my screen better. And so, make my slide advance, please. Sometimes they're slow. The next 5, the remaining ones, up 6 through 10, have prefixes which thankfully make a lot of sense in my thought. Hexane is 6, heptane is 7, octane is 8, and that's what you think of as being in gasoline, actually. It's one of the components of gasoline. Nonane is 9 carbons, and decane is 10. Sounds like decades, sounds like the decimal system of money and things like that. So the names of the alkanes aren't that hard, but you got to get familiar with what they are because they are going to be discussed now and then. Again, these could be described as binary because they're being hydrocarbons means they're only composed of hydrogen and carbon, nothing more. And when they're alkanes, they only have single bonds, nothing more involved. Another way of looking at these is a condensed structure. And the condensed structure sometimes annoys you, but you'll get used to it when you think about it a little bit longer. Methane just has CH4, and ethane is going to have 2 CH3 groups stuck together. In other words, you can think of it as having a CH3 here with a bond between it and the other CH3. So that's another way of representing ethane. Propane is going to be similar, except that it has an extra CH2 in the middle. But again, it's all based on how many total carbons there are. Butane has 2 CH2s in the middle out of its 4 carbons. And then the 2 ends look the same. They're having the same ends that ethane and propane have. And so the longer the number of carbons, the greater the number of carbons, the more CH2 groups show up in the middle. And so if I drew out the butane just to make it more clear, we have CH3 on the end, twice, 1 on each end. And then in the middle we have CH2, and we have 2 of those, and they're shown in this formula side by side. It's a condensed structure. So hexane has even more than pentane, and they all have CH3s on the end. But if you count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, they're all shown in that condensed structure. In case it wouldn't be surprising to you to realize that it's annoying to write out CH2 that many times. So for hexane, sometimes you'll see CH2 with a 4 after it, suggesting there's 4 of them, and then a CH3 on each end for a total of 6 carbons. Okay, that's a quick discussion of names and condensed structures and line structures and molecular structures for the first 10 simple alkanes. Enough of that discussion for today. I hope these things are helpful to you. Please ask questions when you need more. See you in class.